Okay, let's start. Just a quick reminder. So this is what we were doing last time. We're working through this two lectures, which are called segmentation and paging. They are important because those are the two hardware mechanisms which allow us to implement the ideas of virtualization of memory and also provide isolation between processes, right? So last time we discussed that, strictly speaking, you don't need hardware support to implement isolation. You can use these ideas of software fault isolation, right? Remember this instrumentation of the binary, which is used today, which is called WASM or Google Knuckle, which essentially inserts a check in front of every move instruction, and maybe every instruction which acts as stack, and maybe every instruction which does a control fault transition, like a function invocation or a function return, or even an indirect jump. Indirect jump means that the address is not put in the text of the program, but instead is like a register is used to provide an address where to jump, because a priori you don't know where you're jumping, right? Okay, cool. So we know that isolation can be provided in software. Virtualization of memory is a little harder. So remember, what I mean by that is that we would like to be able to implement fork, right? So each program will have its own address 0. And I was arguing on Tuesday that, okay, it's not that trivial, because if you have a pointer which points at somewhere in memory, like copying this pointer is a tricky business, because you have to copy the object itself and you have to patch all the pointers. And in most modern languages, aliases to objects on a heap are allowed, meaning that you have to somehow figure out all the aliases and patch them, right? So that's hard. So that's why, hardware mechanisms like segmentation and paging are kind of a good idea. And they are like extremely popular today. Okay, so we talked about segmentation. So who can remind me what it was doing? What's the main idea? How does it work? Anyone? Cool.
The global descriptor table.
You keep the global descriptor table. Sorry for the handwriting here, which is a table which contains description of segments, right? So, and what is in this table? What are the most important fields in this table? Yeah, base and a size, which I was calling it limit, because this is how it's called by Intel, right? And so how the software and hardware was using this table? Do you remember? Well, remember we introduced special registers. They were called segment registers, like, for example, DS for data segment, CS for code segment, SS for stack segment, right? Mm-hmm. And those registers were holding the indices, which essentially saying, okay, use entry number 5, for example, or in this example, number 0 from the global description table, right? And if you had an address inside the instruction, like trying to move something inside EAX from the memory address pointed by the register EBX, right? What was happening with this EBX? How the global descriptor table affects the value in EBX? You remember?
Describes the offset, which so that would be correct.
Correct. So the hardware takes this base value from the table and adds it with the value of EBX. And this address, which is base plus EBX, is actual physical address, which goes on the memory bus and just fetches something from the memory bank, right? So that was the main idea. It's relatively simple. And what was it allowing us to do is that each program would have a different global descriptor table. Each program would have its own basis for different segments, right? And which means that even if two programs like WC and grep has this register set to 0, because the bases are different, the final addresses which go to the memory bus will be different, so they never overlap, and that's isolation and virtualization of memory, right? Agree with this? Okay, cool. And that's like the slide, which essentially summarizes the benefits here. So we say we have an illusion of private address space. Again, just simple words. It means that each of them can have its own EBX address equal to 0, and yet they are accessing different physical memory locations. We'll fetch different values from memory, right? So we can implement fork because we simply can create a new segment, copy the old segment into the new segment, and patch the base to make sure that the new program accesses the same values, right? And it provides us isolation because if we make sure that bases and limits are configured in such a manner that segments don't overlap, programs cannot access each other's memory, right? And intuitively, we feel that the base and segment for the operating system will cover the entire address space so the operating system can access memory of any program. Can, for example, read arguments which you pass into, let's say, write system call. When you pass a pointer to a buffer, it's in user address, but the operating system will know how to access it, right? Questions?
Why you added the EBX? Why you add this?
Why do you do this?
No, I mean, yeah, move EBX, EBX, and something. Why you use the mark around the EX?
Why do I use them?
Correct. Yeah.
That's all right. So if I write something like EAX, EBX, it just means the value of EBX is moved into the EAX.
Yeah.
If I write its Intel syntax, EAX brackets EBX, it means that the value of EBX is used as an address, and the value from that memory location, which is kept in that memory location, is moved into EAX.
Yeah, why we use the same?
What?
EBX is what's memory address inside EBX?
Okay, let me maybe just get a slide. So okay, this is your memory, right? Physical memory. Starts from 0, goes to some max, right? When you have an instruction like this, EAX, EBX, imagine EBX as this value 1 0 0 0 0, right? So the hardware itself, instead of like moving this value inside the register EAX, right? It goes to this memory location, which is at address X 1 0 0 0 0, right? And whatever the value is there, like let's say 55, it moves this value 55 into the register EAX. So EAX becomes 55, right? Is that the question, or what are you asking?
My question is why you use this to say move the value of address? Why not directly move something from EBX? So what's the?
No, hold on. Like
I know the meaning of this.
Hold on. Like imagine you want to develop a machine which computes something, right?
Yeah.
Like some arithmetic. You have some registers, EAX, EBX. You only have 8 of them, right?
Yeah.
If machine doesn't have any memory, you can only, like, your computation is extremely limited. Although if you ask me a question, and that's a good theoretical question, like, are you Turing complete or not with a machine which has only 8 registers? And maybe you are. That's the beauty of it. But obviously you say, look, it's much more convenient to have this extent, like the abstraction of memory, which saves different large values, right? And then you use those registers as essentially indices to access those values, right? Is that what you're asking?
Yeah, I get your point. Yeah, actually, I can use both the value into the memory, and also I can use it, put it into the register. That's also okay, right? So yeah, my question, exactly question here is, yeah, I don't have any question.
Okay, hold on. Let's take it offline. Like come talk to me next Tuesday, or even like after the class, and I would be happy to clarify anything. Okay, any other questions about this segmentation? Good. Okay, so if I ask you a question now, okay, segmentation seems to be beautiful, right? So, or better than nothing, right? My next question is, what can go wrong? Essentially, like why this mechanism is not ideal. And when we finish with the paging, we can come back and reevaluate the argument why paging is not ideal and why segmentation might be superior in some cases. But let's talk about the segmentation first.
If one of the processes needs to get more memory.
Right. So what you're saying, like, imagine this green one says, okay, that was my heap here. It was growing this way. And at some point, I really need even more heap, right? Like with segmentation, it seems to be like relatively straightforward. You say, look, I will just fix the limit. And it works for a while before you run into like a physical memory of another segment, right? So not ideal. Again, you can fix it. You can say, look, I'm so smart. I will just rearrange the segments in memory. I will move them around and I'll figure out this space, right? Right. So you can like move the yellow one a little bit. But obviously copying large segments is not ideal because it takes time, right? Right? You can say, okay, look, I'm so smart. I will just even implement this idea of swapping to disk. So instead of like moving it in memory, I say yellow will not run for a while. That's my prediction. So I will just copy the entire yellow segment to disk, right? So it also works. So like, I just wanted to make sure that all these ideas can be built without paging, right? But again, overall, it becomes cumbersome and hits some performance limits. So you really want to be able to like to control your address space a little bit faster for those cases, right? And okay, so this idea is like your memory gets fragmented, you have gaps and stuff like that. And so people suggested, okay, we get it. Like as programs were getting more and more complicated, address spaces were getting larger and larger, segmentation was hitting its limits. And the idea which all CPUs are using today is called paging. A high-level trick with pages is that the virtual address space of the program is split into equal chunks, which are called pages. Pages can be like on different architectures, can be of different size. Like let's say most typical page size is 496 bytes, right? And then those individual pages are mapped to different physical locations, meaning that, for example, this page is mapped here, right? This page, which is consecutive in the virtual address space, can be mapped to a completely different chunk of physical memory, right? This is your physical memory and this is your virtual memory, right? And similarly, this like continuous physical pages can belong to different processes, right? So you can like map them and say that like the next two physical pages will belong to the yellow process, right? And there is some data structure which CPU implements, which implements this mapping, right? And the operating system controls this data structure, similar to how it controls the global descriptor table. It controls something what is called a page table. And by configuring the mappings, obviously, you will achieve isolation and you will achieve virtualization of memory, saying that, okay, like the page which sits, the virtual page which sits here at the address 0 will be mapped somewhere, and that's fine. When the program issues 0, it really will access some address here, right? So if you access some address with in an offset of a page number 0, you will land here. If you access address 0 in the yellow process, again, the mapping will be different. So let's say somewhere here, and then the real physical location, which backs up this virtual page, will be somewhere here, right? Got it? So the high-level idea is elegant, right? Now you control the mappings at the level of, let's say, 496 bytes, right? And as I said, the size can be different, right? So modern hardware can support, depending on the architecture. So 32-bit Intel supports for kilobyte pages and for megabyte pages, and modern 64-bit machines support 4 kilobyte pages, 2 megabyte pages, and 1 gigabyte pages, right? And I will explain later why we need different sizes. It's, again, the performance reason is there, right? But we control the mapping for each page independently, right? Which gives us a great degree of flexibility, right? So we say, like, we wanna one more page to allocate for our heap because someone does a malloc. We just find an available physical page and map it, right? And we don't need to move anything, right? Okay, if we understand the high-level idea, let's think of how we can build this mechanism. Again, let me be clear here that when I talk that CPU supports something, think of a CPU as of something you can program, meaning, like, obviously it comes as a collection of fixed gates which are manufactured, right? But originally all the CPUs are programmed, right? The programming language can be different from C, and in fact it's different. But there are flavors of those languages which are kind of close to Java, right? So you can think of, I take a language, a Java-like language. Well, Java is a little, maybe a stretch, right? So, but like you guys maybe use those languages, right? But essentially you can program anything. So if you want to have a hash table, you can program it. It will be implemented as a collection of gates on the CPU, but it's like, to you, it doesn't matter. Like, yeah, if you care about optimizations in a pipeline, you have to be careful, but otherwise it's programmable. So that I just wanted to make sure that any data structure that you desire, you can program and CPU will support it. You want a linked list, you can program a linked list, and the CPU will traverse the linked list. How can we build this page table? So what's the data structure? What will be the candidate for us to do the mapping between a virtual page to a physical page? An array. Okay, that's one candidate. Array is an obvious candidate, right? And it's very easy to begin with, right? So you say, look, let me just explain how array can work, right? So you say, I have a virtual to physical translation array, right? It has elements. My high-level goal is to translate every virtual page into some physical page, right? I'll first ask a question, how big, what will be the size of this array? How big it should be? How many virtual pages are possible for me on a 30-bit?
4 gigabytes.
A page size is 4 kilobytes. You have a 32-bit architecture, so you have 4 gigabytes, right? If we divide 4 gigabytes by 4 kilobytes, we actually get 1 million.
Yeah,
Right.
yeah, yeah.
And so here we have 1 million different pages, starting from page 0, page 1, page 2. Each of these are 4 kilobytes, right? Okay, so cool. Our array has to be 1 million, or more specifically, this is the number if you do like power of 2 correctly division and everything like that, right? So you say the entry to this array is the number of a page, right? Because we say we will translate page 0, for example, and the value inside the array is the number of a physical page. Let's say in this example, for the page number 1040, the element of the array contains 12, which means that the page which sits here, which is 1040, is mapped to page 12, right? Agree with this?
Yes.
Reasonably easy. And again, where do we get these addresses, right? So let me just clarify a little bit. So imagine you have an address, like, let's say again, move instruction, something into the EAX, and the address which you're using for the move is this address, X410010, right? If you translate it in binary, you will see that it's actually 20 bits. Okay, why 20 bits? Let me just, it's probably worth spending like a second on this slide because
The total is 4 kilobytes and each equation 4 kilobytes.
hold on, look, the total letter size is 32 bits, right? One page is 4 kilobytes. To address any byte within 4 kilobytes, you need how many bits? You need 12. So all these 12 bits control the offset within one page, right? Which means that all these upper bits control the number of the page, right? So correct. So, and in this specific example, if you take those bits, they come up as, the whole address comes up as 410010, but the page number itself are those 41410, right? Which in hex, and in DEC it's 1040, right? And that's the index. So you say the upper bits of the address are effectively a page number. Do you get this idea, right? And you say, look, I'll take the page number, I will use it as an index into the array, and whatever is there in the array itself, like 12 in this example, will be a physical number of a physical page. Or let's say not a physical number, but a physical page number, right? Starting from 0, right? Agree with this?
What are the elements?
Elements, that's a great question. What are the elements? So roughly speaking, since you really wanna say, like, I have some number of physical pages. I don't know how big is your physical memory. Maybe it's less than 4 gigabytes, right? So typically it was less, now it's bigger. So, but you say, and the major thing is the physical page number, right? That's what you want in this array. But maybe you want something else. Maybe you want access bits like readable, writable, user accessible, or only kernel accessible, right? So that gives us, it will, if we answer a question like what's inside this array, right? So how many bits we really need to represent a physical page number? Well, we already just talked about it. It's here.
More than 20.
20, exactly 20. So if we have an entry, so the minimal entry which we need is 20 bits, right? But as I said, okay, look, but maybe we need some access flags as well here, right? So like read, write, executable to make sure that we cannot accidentally execute stack. We want to protect against the stack overflows and stuff like that, right? So you say, okay, an entry will be maybe 32 bits, just 20 bits for the actual physical page number, and the rest, the other 12 for various flags, right? Agree? So again, just to judge the size of this array, right? So we have 32 bits, which means 4 bytes, right? And since the array is 1 million, so the whole size of the array is 4 megabytes, right? Right? Okay, CPU can do it, but it becomes a little bit awkward, right? So because as we just discussed, the size of this array is 4 megabytes. So it's a little, again, when I was starting I'll tell you, I think my first machine had 16 megabytes total of RAM, like Pentium 1, super cool. Eddie gave you one that was mine. But of course, that's not very practical, right? Because if you say, look, if I have this array and suddenly, it occupies like 4 megabytes here, that's a bummer, right? And essentially, I have a couple of slides explaining that it's a bummer, right? So I have this logic saying that we need 4 bytes to relocate each page. So essentially 20 bits of physical page number, 12 bits for access flags. And the whole array is 4 bytes by 1 mil, so 4 megabytes, we just discussed it. And if I put it in memory, so the hardware, for example, has a register, which in practice on Intel, the register which holds the root of the page table is called control register 3, CR3, right? And so if you say, look, in physical memory, this array occupies 4 megabytes, that's not the greatest idea, like especially 10, 20 years ago when these data structures were designed, right? Okay, everyone is on board, not great. So what's the next improvement? How can we improve? Like, we have an array, but it's big. So what can we do? How to make it better, more practical? You have an idea? Go.
I have a question.
Yeah.
What's CR3?
CR3 is just a register on the CPU, which operating system controls, and it stands for control register 3, and it holds the physical address of the beginning of the page table. in my current illustration, it holds the beginning of the this array which we're discussing. In practice, it will be holding the root of the data structure, which will be describing the translation. Right. For now, in our current attempt, it's an array.
So it's only one value or many values.
It's just one. The hardware knows, okay, I know where the beginning of the array, you give me the index, you say your index is 1040, right? So I know where the beginning, so I will add 1040, multiply by the size, I will land on this entry, right?
So it's kind of like a global address.
Yeah, it's a physical address,
Okay.
which operating system controls, right? And when you start a process, you say, look, I have a new array, I will set this CR3 to point to the beginning of this array, and I will fill in all the entries in the array, so my virtual memory is ready. So, okay, what's the next improvement? Array is not the greatest thing. What's next?
I think arrays is still possible because we can allocate as dynamically. And you said we allocate for multiply, but
Got it. Okay, hold on. So what you're saying, can you kind of like following my slides, which kind of, scares me a little, because really I expected a hash table or something, right? But what you're saying is that, look, maybe I don't need the entire array, because if I run a small program like WC, maybe this part of the address space is never used, right? And I will be just having array with size, right? And I will allocate the array as I go, right? Is that your idea? Okay, so I have a couple of slides here. So specifically here, array with size, that's what we're talking about. We hold the size, we say max element of the array 2047, and so it may be occupying just a couple of physical pages, right? That's not bad. That's definitely an improvement, especially like if you start with a small program, as your address space is growing, you might allocate additional entries in the array, right? That's what you want. Okay, so what is the disadvantage of this data structure? Although it clearly seems like an improvement, but what can go wrong with this one?
How do we store the array?
We store it in physical memory, obviously.
Right, but when we're paging.
Well, that's a good design decision, whether you can page this data structure or not. Maybe not. Like we can get to the details of it later, but definitely instead of occupying 4 megabytes immediately, it occupies less, right? So it will be less than 4 because we have a size, and our size is right now 2047, right? So is it a good data structure or not? Yep.
they have similar problem you mentioned in the segment because they are contiguous and then.
Right. What you're saying is that it has a similar problem because you say as we grow this array, maybe we will need to allocate additional physical pages here, right? And maybe we will run into the fact that something is already occupied in this region, right? Agree with this? Not ideal, right? And just to give you a couple of other examples, like imagine at some point your program says, okay, I want to go through some stage of maybe running through a giant amount of data, allocates a huge array, like half of the max size, 500,000, right? And then immediately deallocates some parts of this array, right? You say, look, there are gaps of memory which were occupied by my data structures, trees, hash tables, whatever you wanted to use in your address space. And now they are not used, right? But the array will still have to hold the max address because this addresses here at the very end are still used, right? So there is like a little bit of this like problem of a gap here, right? So if you have a gap in your address space, you still over allocate, right?
Yes, our option is we can
Correct. So, but do you see like if you're a hardware designer, you're designing a CPU, you say, I want this data structure. Like, what's your next step? How would you improve it? So right now you have kind of array, but it has these unused gaps, and you think, okay, I don't really want to hold anything for those gaps. So what would be my trick?
Use multi-level page tables to divide the address space further and leave the upper entries blank. If you're not using like the second chunk, have the second entry be blank.
Correct. And this is what exactly is done. So, but I just wanted like gently to guide you to this idea, to give you like, okay, I know multi-level page tables, but I wanted to understand why we arrived to this idea. So a multi-level page table is really an array of arrays. And so you look at this and you say, look, guys, I want maybe to have something to translate regions, and then I want to have gaps. And you say, okay, I will have a first level, which is array of array. And you say, if there is a translation for a specific region, there will be a part of my translation array which backs it up. And if there is none, this gray, which like responsible for this region, then there is no array which explains the translation of the region, right? Which means that okay, let me explain a little bit better how it can go. So like you say, look, you have an address, you have a top level page, you have a top level data structure, which is array of arrays, meaning that this array holds pointers to chunks of your translation array, and not all chunks have to be present in the system, right? And those chunks, if you carefully choose the sizes, let's say each chunk is 496 bytes, it fits in one page. You say, look, I have a translation for this, for the region, like for the index, let's say, for the index 01, for the index 1. And for the index 1, I will have part of my translation array. For the index 3, I will have nothing. So this space is never, like none of these pages is used for representing translation of this region. For the index 3, I have again, like bits of my translation array, which sits in a physical page 9, for example, right? Do you get this idea how it works? Let's hold here, because this is how the page tables are really implemented. And the hardware, for example, says, okay, I will hold my control register 3 will hold a physical page number. In this example, it's physical page number, which equals to 2. This is the physical page in which the top level of this data structure is stored, and it's exactly 4096 bytes. It fits in one page, right? And this is array which contains pointers to other chunks of this translation array, right? Too complicated or like obscure a little? Like, hold on, let's go step by step. So remember, my goal was not to keep the translation. If this is my translation array, my high level idea was to avoid keeping gaps, because if I don't use anything, I don't want to keep this array around. So now I keep array as a just disjoint sets of arrays, right? Each array is relatively small, it fits in one page. If my address space uses this virtual address, I will have an array which explains how to translate it. And this top level data structure tells me whether I have the translation or not. So in this example, yes. And it says, okay, if you're translating the address which falls into the specific region, the chunk of the array is sitting in the page number 8. So this is page number 8, and this is my translation array here, right? Agree? And let me just go over a complete example. But this is exactly the intuition why you might come up with this data structure. Because if your address space is extremely small, what is the size of this data structure? You definitely need the root, because it's always present. So it's 4 kilobytes and maybe nothing else. Maybe just one chunk is enough. Each chunk is also 4 kilobytes. For a very small process, the whole page table will be just 8 kilobytes, because you need the top level and one small chunk of the translation array, right? So that's a big savings compared to like 4 megabytes upfront. Agree with this? Okay, so let's do an example. And this is really how the page tables are implemented by modern CPUs. So again, we have an address here. So again, we have AT&T assembly, which moves something from the, if I rewrite it in Intel, it moves inside EAX, the value which is at the address pointed by the EBX register, right? And the EAX right now contains 0, and EBX contains this decimal value, 20,983,809, right? If you encode it in binary, this is the binary encoding. And I split it, the total is 32 bits, but I split it into like 12 bits, which are the offset within the page, and this top 20 bits. And the top 20 I split into 10 and 10, which will become clear why in a second, right? So the hardware, let me maybe spend a little bit of time and explain those sizes, right? So we all get the point that the 12 bits contain the address within one page, right? Is it clear? Because there are 4,094 bytes, and you really exactly need 12 bits to encode any, like from 0 to 4,090, what is it? 96, 97, right? What's the size? 496, 495 then, right? Is that the correct value?
No.
Yeah, so starts at 0, ends at 495, right? Okay, cool. Then if we take this, if you take my top level data structure, which I was trying to, like, this index of arrays of arrays. I'm sorry, wide. If I want to fit it in a page, right? So the total size of the data structure is 496, right? I agree? Because I will explain this design choice, but I want to fit it in one single page. So if each entry is 4 bytes, because I want to contain physical page numbers of the pages which contain next level, right? So it's 20 bits plus access flags. So let's round up to 32 bits, 4 bytes, right? So each of this page itself contains 1,024 entries, right? Agree? And so how many bits I need to address any entry within an array of 1,024?
10 bits.
10 bits, exactly. That's why I say I will use the top 10 bits to choose one entry in this top level. So if all of these bits are zeros, I will choose entry 0 because I say, look, this top essentially, like if you have one giant translation array, which we don't want to keep in memory, now we split it in 1,024 different chunks, right? This is chunk 0, this is chunk 1,023, right? Then you say, look, each of these elements is either a pointer to a page which contains chunk 0, chunk 1, and so on. And you can say, like, there will be a present bit, whether the translation is present or not, right? So then you say, okay, cool. So like, I really like the bit which sits here chooses the chunk. So in this specific example, the whole value of this 10 bits is 1. So it chooses chunk number 1. Agree? And then you say, look, for this chunk number 1, do I have a translation? Like, do I have a chunk of translation array, right? So, and that's why it works this way. So again, so here we say, look, the address is like that. I split it into 10, 10, and 10, and the top 10 bits choose an entry in my top level page table, right? So the hardware itself will say, look, so here I am, like what I'm trying to explain, that this top 20 bits are a virtual page number, right? And the hardware itself will essentially translate from the virtual page number, which in our case is 5,123, right? Those are the bits 101, so 101, and then the other ones 000, and the bottom one 11, right? So that's exactly those 20 bits of the address, right? Let me just erase everything here. So this value is specifically this value, right? So the hardware itself says, okay, I will contain the address of the top level of this arrays of arrays. And in this specific example, we say the CR3 will contain address 0, which means that the page table sits here, right? And it's just OS operating system chose to put the top level of the translation array in this page, right? So physically, it looks like that. CR3 points to physical page 0, and this physical page 0 contains the first level of translation, right? Now we say, okay, look, we use the first 10 bits, which are those bits, and the value of those first 10 bits is what on the screen right now? You can tell me who can read from binary to decimal?
5.
It's 5. And that's why we say, look, we choose entry number 5, right? So this entry. So if I ask you what this entry contains, do you remember still from my previous? What's the value? Page number, which page number? Say again, physical page number, which of what?
Of the corresponding of the second level.
Correct. So specifically, let's say it contains 7 in our example. Operating system configures this number, sets 7, and which means that in a physical page 7, this chunk of the translation array which we care about is contained, right? Okay, cool. Now we say, okay, by the way, like which element of this array we're trying to use, right? So each of this encodes, again, one of 1024 numbers, right? So it's each individual page, meaning that the top level encodes each of these regions is 4 megabytes each, right? And you have thousands of those. So the whole thing will encode all 4 gigabytes, right? So essentially top level kind of controls a region of 4 megabytes, right? And the bottom level contains really, okay, my pen stopped working just out of nowhere. Why? Just because. And the bottom region contains like again 1024 entries. Each entry is 4 kilobytes, so it's essentially describing each individual page within a region of 4 megabytes. Is that clear? And I don't really know how to fix the what's wrong. What's wrong with Mac? That's what the question. Let me just quickly try to disable Bluetooth. Yes, no, no. Really? Yeah, no luck. So we will continue like this then. Okay, so now we take the next 10 bits here. The value here in binary is 3. So we will choose an element number 3 in this second level, right? Because it specifically just says, okay, like tell me where the virtual page number 5123 is located in physical address space. And if the operating system puts 12, it means that really this page which we're translating is page number 12. So at a high level, what we achieved is the following. So this page, which is page number 5123, is backed up by the physical page 12, right? And now we have the last step of this translation. We say, look, what is the offset within a page? So we take the last 12 bits here, and it's byte number 1, which means that we're going to read byte number 1, not 0. And essentially at this point, we say, okay, this value 55, which is contained in byte number 1, will be loaded in the register EAX. That's what we wanted, right? So, okay, so this is how it works. Now probably time to ask questions. Is it relatively simple? really, really hard.
So what it looks like, trying to reduce like the space of this thing, we instead turn it into 3 different numbers.
We turn it into what, 3 different?
So first you have to.
Correct. Yeah,
Yeah.
correct.
So is that worth it?
That's a good question. That's actually a great question. And originally, CPU designers said it will not affect your performance because we will implement a specific data structure on the CPU, which is called translation TLB, translation look aside buffer, which will be caching frequently accessed translations. So if you frequently access the page 5123, the very first time you really have to do all the 3 memory accesses, right? So like there's 2 additional ones to look up the page table. But then the hardware on the CPU will remember that 5123 is mapped to page number 12. And so that will be available to you in one cycle. But there are some additional complications with that. We'll discuss in a second. So on the surface, almost fell. On the surface, it looks like it's reasonably benign, but there are some workloads which can be affected by the page table lookups significantly. And that's why in the later versions of the CPU, they actually said, okay, it's so expensive that we will, if you really use huge memories, please use big pages. Meaning that I will talk later about it, but on 32-bit machines, instead of having 2 levels of 4 megabyte pages, will require only 1 level of array, right? And if you have 64-bit machines, extreme case today is 5 levels, because like up until recently it was 4 levels, and now the most recent machines have 5 levels. So yes, and then it's not even like 2 additional lookups, it's 5. And if you're running a virtual machine, you will end up having another 5 underneath. That kind of scares you in a data center. But okay, cool, yeah, that's a good question. Is it worth it? So in a second, we will discuss a little bit more. So there is really a performance trade-off. And that comes back to this argument, other segments that bad? Because segments were blazingly fast. You have just one register, data segment, and an entry in the GOT, which can be easily cached on the CPU. So clearly it's very, very fast, right? But again, let's ask a couple of naive questions. So do we understand how translation works, right? Do we understand why this top 10 bits decide the entry? Why is it we split it into 10, 10, and 12? Do we understand this? So the top 10, like roughly speaking, again, so the top 10 decide which region of 4 megabytes you're trying to access, right? Because the whole address space now split in 4 megabyte regions, and you decide, okay, this top 10 addresses says, okay, which region are you trying to access? You say, well, region number 5. And you here in this entry, each entry of this one is responsible for pointing you to the part of the translation array, which is responsible for translation of that region, right? And you say like, well, if this entry is present, then I can go on and translate, right? I can go read the next level. And then this next level, since the whole size of this region is 4 megabytes, it has 1024 entries, it naturally represents individual pages, which is like 4 kilobytes each, right? So that's nice. So essentially, and you just choose one of those with the next 10 bits, right? And if it's not present, then it's a page fault, actually, because this kind of a fault is called a page fault. So the hardware says, okay, I'm trying to go through the paging. The next level is not present. So here's a page fault. The operating system can handle it. Maybe can bring a page from disk. Maybe can say, well, it's time to crash. And that's why you see a segmentation fault. Okay, so good. We understand the array. Question?
We have the for the whole system, we have only one physical page table. So how about the isolation? Even processing the.
Yeah, let's discuss isolation in a second. So you guys have a question? Ask me. Do you have it? No. Then, so raise hand, ask question. Do you have a question behind? Okay, good. So let me just go over one more time. So the entry to this translation is CR3, right, at the bottom. It has a 32-bit, so it's a physical address of the root of the page table, which is called on Intel page table directory. Then we take the address, which has 10, 10, and 12 bits, right? And those 10 bits, the top of the address, decides the entry in the page table directory, right? This entry itself, what does it contain? So I kept saying that it contains the physical page number of the translation array and additional flags, right? So really this address is only 20-bit, that because we only have 1024 entries, right? And 20 bits are sufficient. So that's why additional bits here used for like different purposes. And there is a couple of interesting bits here. So for example, this bit, the bit number 0, decides whether the translation entry is valid or not. It's called a present bit. So this bit number 1 decides whether the page is readable or writable. The bit number 2 decides whether the page can be accessed by the user code or not. If not, only the kernel code can access the page, right? And such, like other bits, we will like probably skip, but like you get kind of the point that those bits, those flags are important. Question? You have a question? Okay, so this is the entry. This is specific format of the entry on Intel, right? So then we say, look, from here, we got this 20 bits, which is a physical page number of the next level of translation, which on Intel is called a page table. So this is page table directory. This is a page table. A little like I keep saying page table is the whole thing, but really Intel originally was calling this a page table, right? And this 10 bits from the middle of the address, those 10 decide specifically which one of those entries should be used, right? And again, the format of this page table entry is very, very similar. It again has 20 bits of the physical page number and additional flags, which keep like whether the translation is present, bit number 1, whether the page is actually readable or writable, whether the page is user or only kernel accessible. There's a couple of interesting bits here. So the dirty bit means that the page was actually written. The hardware keeps track of which pages were written, which means that the operating system actually has to save them to disk if something important happened, like if it's like part of the file, for example. And if it's not, it wasn't written, then it can be just thrown away. And whether the page was accessed, this bit is used to identify a set of frequently accessed pages. And then you say, look, if I'm running out of memory, I have to take some of those pages down to disk. By collecting statistics about how frequently the pages are accessed, you can say, okay, there's the least frequently accessed pages go to disk, for example. This is how paging works, right? Okay, we got it. And at this point, we figured out the actual, this 20-bit will give you the physical page address of the actual page, right? So this is the, like, if you say that this was my virtual page number, let's say 10 or something, right? Those 20 bits will give you the physical page number. Maybe it's page 55, which contained the virtual page 10, right? And this last offset bits will actually decide the offset within the page, right? I just walked through this translation one more time, and this, like those diagrams, they're taken from the Intel manual. So again, if you open the manual, you see those pictures, you know that, okay, you know what it means, right? Any questions about paging? Each process will have its own page table. I'll talk about it in a second. Good question. So that's what you're asking? Yeah, let's see how it works. Okay, so just since you already asked it, so what are the benefits of page tables, right? So compared to arrays, right? So the page table, this data structure, allows us to represent a small and also sparse address space. Maybe you're using just a couple of pages in the entire address space. Maybe a couple of pages are in the beginning address space at lower addresses like 0 and so on, right? And maybe some pages are at the higher addresses, right? But you don't care, because really, if you have an address space which has only 2 actively used chunks, you will have only one top level and 2 bottom levels to translate those 2 different chunks, right? So the total overhead will be 4 kilobytes multiplied by 3, so like 12 kilobytes for the page table, right? So that's great. And as the address space is growing, of course, you allocate more and more entries in this translation array. And in a max case, you will have to translate the entire address space, and you will be back to the same 4 megabytes plus 1 top page, which is 4 megabytes plus 4 kilobytes, right? So it's even a little worse, but this is so rare, especially in the days where the physical memory was expensive, because typically a physical memory was like initially like 16 megabytes, then like 128. Now it's in the order of like 10 years ago, it was in the order of gigabytes was a good laptop. Now we're buying laptop was like 8, 16, 64 gigabytes, right? And servers can reach up to like terabytes, right? So now physical memory is way more cheaper. So the paging rates are like, again, it's not a surprise that your web browser will easily use a megabyte, or not a megabyte, a gigabyte of physical memory, right? To just show you whatever you want to see. But as we say, like nothing has to be allocated upfront. And like essentially, but it provides the same flexibility as the array, right? If we go back to this question of how do we support isolation, right? So we have to program 1 memory, right? At this point, the guess will be that each process will have its own page table, right? So in my example here, I have a green one, which has its own page table, which is configured by the operating system when the process starts, right? When we do exec or fork, when we clone the same one. And the purple one has its own page table, right? And the mappings of those page tables are typically done in such a manner that the purple physical pages do not overlap with green pages, right? And also I keep mentioning that the operating system is mapped like the same physical pages, like which are used by all processes. Like all processes use the same kernel. So if this is the page, for example, the same page here, and is backed up by this physical page, for example, will be mapped in each address space. And that's convenient for system calls. We will come back to it, right? But I say, no matter which address the green process uses, the green page table will land it on one of those green pages in memory, and it will never be able to access a purple page of the purple process, right? That's how isolation works, right? If you want to load a library which is shared between multiple processes, right? You can do it, right? So you can say, wow, by the way, this chunk, which is occupied by the text section of the library, will be mapped to the same set of physical pages in all address spaces, right? That's how you implement sharing of this printf function, for example, right? Okay, so this is good. Again, compared to segments, we have like a couple of additional benefits, right? So we can say, look, we can actually emulate a way larger address space, virtual address space, on top of a small physical memory, right? In the example which I was showing on the screen, I only showed like 12 physical pages, extremely small machine, right? Unrealistically small. But you can still emulate the all 4 gigabytes, or yeah, because you say, look, if the page is not present in the translation array, it's a page fault. Operating system handles the page fault, goes to disk, finds a available physical page,